Welcome back. This video is going to be the second part to the previous video which I published. Last time I described why I made IMX219 camera module to fit on this lattice MAC X03 FPGA board. In this video we are going to take a look how I implemented MIPI CSI 4-lane receiver on lattice MAC X03 FPGA and streamed video data over to the USB. On the left hand side you can see there is one default configuration IMX219 camera connected to a Raspberry Pi 4 board, and I have soldered this 0.1 inch female header so that we can easily probe and get a proper ground connection to view the high-speed MIPI data. This video will go further into detail how this IMX219 camera sensor work, how clock system of IMX219 sensor cam works, and how we can program the sensor to fetch correct frame rate out of it. What are the limitations of these type of camera sensors when compared to small camera modules which I have been previously using. When I compare this camera sensor to a camera module, something like OV7670 or OV2640, the last camera which I used, PE1005S, in comparison to those camera, this camera is quite bare bones. There is not much signal processing going on the die itself. Most of the signal processing is supposed to be done at the receiver end. The camera sensor silicon itself has sensor element with Bayer filter on it, a ADC to perform analog to digital conversion, clock system and MIPI output generator, and a control system which can be configured over the I2C. As I have already mentioned, my goal is to connect this camera to a USB and stream raw YUV data over the USB 3.0 connection. But the problem is this camera sensor does not output YUV. It does not even output RGB. It outputs only raw Bayer image. And what does raw Bayer image means? To know more about Bayer filter, you can definitely refer to Wikipedia. What it basically does is this sensor at silicon level had only a grayscale sensor array, and on top of that grayscale sensor array, a physical color filter has been put, which is in the form of red, green and blue color filters on alternate pixels. Bayer filter can be arranged in many different ways. You can refer Wikipedia for more information about it. So output of IMX219 is Bayer filtered raw ADC results. So to be able to convert it into YUV, we first need to perform a de-Bayer filter operation. We need to demosaic the image and get the color information out of the Bayer image. And after performing de-Bayer, we will have RGB. And from that RGB we will need to convert to YUV before we can send this YUV data over to the USB. What else these kind of camera sensor does not have when compared to finished camera module is the capability of performing any kind of auto exposure or white balance. So host application must regularly look at the image, how bright or dark it is, and adjust the gain setting and exposure time accordingly. Camera sensor have on-chip PLL to generate MIPI output clock and ADC clock as well. So you need to supply a slow external clock, and camera sensor PLL will automatically generate hundreds of megahertz of output clock and the ADC clock. As part of the configuration of the camera, we will need to set those PLL multipliers depending on the output clock and frame rate what we want. What else we need to set is output resolution, and depending on the output resolution, the sensor crop size. On the left hand side you can see this camera sensor is connected to a Raspberry Pi 4. Now I'll start a recording on the terminal 1080p at 30 fps, and we will look at the oscilloscope. How does the camera outputs the raw data? Now on your screen you can see screen capture of my oscilloscope. On channel 1 I'm capturing MIPI clock, channel 2 MIPI lane 0, and channel 3 is MIPI lane 1. All three are looking at the positive line of the differential signal. This is how it looks once the capture is started. On the bottom left corner you can see the DVM frequency is saying 30.006 Hz. This is the frame rate. DVM is counting on channel 1, which is the clock line, when it enters and exit HS mode. Let's zoom it a little bit. This is how a single frame looks. This is how start of the frame looks. Here what you see is the first line, and here is the embedded line information, and very tiny little small packet in the beginning. You see there are 3 packets, and the small one is the frame sync packet. Right now on your screen you can see this is the packet specification of the CSI. It's supposed to send the frame sync, embedded line information, and then comes the camera sensor output. And here in the beginning is the frame sync, embedded line information, and here starts the display line. We can definitely count how many display lines are coming in. Let's zoom out a little bit, add a measurement. I have set up a measurement to count how many lines it's sending. So you can see here it is sending 1081 lines. Right now you can see on your screen capture of the I2C bus. We try to record video from the terminal. This is how the I2C bus get access. Let's decode it using protocol decoder. Let's start from the start. Address 64, as you may or may not know, this little camera module from the Raspberry Pi. Other than camera, it has one I2C encryption chip as well to detect if camera is from genuine Raspberry Pi or not. Raspberry Pi people didn't want other people to manufacture cameras for Raspberry Pi, so they have put this encryption chip so that it will be harder to make compatible camera for Raspberry Pi. And I believe these initial address is 64 is the address of that crypto chip. As we are not interested in that crypto chip, so I'll just skip this part. Let's scroll down. Here is the first access to the camera at address 10. Let's scroll further down. Address 10, register 103 is written 1, which means software reset. Let's scroll down further. Register 100 is written 00, which means camera sensor will be in standby. Let's scroll down further. This register 6620 I believe is the part of the register access sequence along with 30EP. Datasheet of the camera describe this register access sequence. We must send these bytes at these specific addresses. Register address 114 is the CSI lane register. How many lanes we want? It says 1 means 2 lane. If we were having here 3, it would be 4 lane. 128 is DPHY control register. 00 means auto mode. The complete description about these registers can be definitely found in the datasheet, and default values can be found in the IMX219 driver, and the complete initialization registers sequence can be found in the IMX219 driver in the Linux kernel repository. You can see this is all access at address 10 and various registers being initialized. I believe at some point here it had started to stream because it is repeatedly sending these commands: 157, 160, 162, 15A. 15A is to set integration time, 157 is to set analog gain. I'll talk about this thing later. Right at this point, register address 100 to 1, camera will start streaming, and you can see as soon as we start streaming, the host starts sending these commands: 157, 160, 162, 15A. 157 is to set analog gain. I believe it is a part of the auto exposure control, as camera does not have auto exposure. So Raspberry Pi continuously sends this command 0157 along with 160, 162, 15A. Register address 157 is important to do auto exposure, and I believe register 015A is also important as it sets the integration time. The more the integration time, you can see they are coming repeatedly at a frame interval. You can see data at address 157 is changing depending on the scene, and data at 160 and 162 remains stable, remains constant. When I was recording videos with Raspberry, register 160 and 162 always remains constant, while 157 constantly changes depending on what the camera looking at, how bright the scene is, and register 15A in most of the settings it always remains constant except for the 1080p video at 30 fps. It varies between minimum around 024A and maximum 06DF. Let's look further into detail how exposure setting changes during the recording. Now let's look at the I2C activity during the video recording. I'm recording 1280 by 720 60 fps video, and as I have already mentioned, camera itself does not have any auto exposure capabilities. So during the video recording, exposure setting must be continuously sent from the host side to the camera. To test this, I'll be moving this bright flashlight in front of the camera, and at the same time we will look at the oscilloscope how the analog gain setting changes. Let's look at the scope. You can see on your screen oscilloscope view of the I2C capture. The register address 0157 hexadecimal is being updated. Let's move the flashlight in front of the camera. Now I am moving the flashlight in front of the camera. You can see the register data is being updated. The bright light from the flashlight has completely overwhelmed the camera. So you can see the analog gain setting has went down to completely 0. Let's move it away slowly. And now let me cover the camera with my finger. I have covered the camera with my finger. It appears to be hexadecimal E8 is the maximum. Let's try one more time. I'm moving my flashlight in front of the camera. You can see the analog gain setting value is changing as I take it closer. Analog gain setting goes lower and lower, and flashlight is directly focused onto the camera. It settles to 0. Along with the constantly updating analog gain settings, Raspberry Pi also writes these 3 registers. Register address 0160, 0162 and 0158. These are frame length, line length and integration setting. They are constant. I don't know why Raspberry Pi sends it, but it sends constant value regardless of what the camera looking at. You can see it does not change. Flashing my flashlight onto the camera regardless of what I do. Integration time, frame length and line length does not change. Let's try to change the video settings. Integration time is really important for the frame rate. So I believe if I change frame rate, integration time will change. Now I'll be changing it to 30 FPS at the same resolution. I have changed the video setting 30 FPS at same resolution 1280 by 720, and you can see integration time has changed to 0633 from 0200. Let's look at the hardware solution, how I have put everything together. I have mentioned in previous video, the first attempt of making an interconnect board to connect everything together was quite a failure. So I have made another PCB to connect everything together. Does not have any connection for the camera itself. Camera directly connects to the FPGA board. Something like this. This module goes right here on the front of it, and because of the MIPI signal integrity, I will remove all the headers which connects the camera, and those pins which connect to the camera and they are high speed, they will never ever touch this board. So on this board, on the one side there is a place for USB port. The USB FX3 board goes like this, and on the other side connects the FPGA board like this. This board is only supposed to connect the FPGA board and the USB board. The MIPI signal never touches this. Let's see how it fit together. This is how camera is mounted on front of the FPGA board. And if you look at the left, I had to remove all the headers which connects the LP lines as well as the HS line of the camera, because I don't want any headers to function as an antenna, make any reflection point in the signal. At this speed, every millimeter of the extra trace is important. You can see right through it. I have cut the header so that the HS signal never need to travel to the baseboard. On the back, you can see this is the baseboard which is mounted. This baseboard also have 2.5 volt VDD IO regulator for the MIPI IO bank, as the latest Mac X03 FPGA board only have 3.3 or 1.2 volt IO regulators. The MIPI signal need 2.5 volts. So I have mounted the regulator on this baseboard. USB 3.0 volt from the Cypress is also mounted on this side and supplies power to the 2.5 volt. 32-bit 100 MHz data bus connects through the interconnect port to the FPGA. Let's program everything and take a look how does it work. Camera is focused onto my workbench. Let's start streaming from the camera. Right now I have configured the camera at 1280 by 720 pixel and 60 FPS. Let's start the stream. You can see picture is reasonably clear, although I'm not quite satisfied with it. There is definitely some room for improvement, so I will definitely do further improvement. On the right hand side you can see there are 3 controls possible: brightness control, contrast control and the gain control. Gain control is actually not real control. I have set this gain control to toggle between different test patterns, and let's look at different test pattern. Test pattern 0 means test pattern disabled, and I'll move to test pattern 1, which is completely blank with a solid color. Right now it's set to black. Let's move to test pattern number 2. This is the test pattern number 2. You can see it's perfect. Let's move to test pattern number 3. This is how the sample test pattern number 2 is supposed to look, and this is how it looks. If you look carefully, though the colors are perfect, but if you read carefully, you can look that some colors are inverted. The problem is with the debier filter. Actually, I have found some discrepancy in the data sheet. Overall, in the IMX219 data sheet, it does not directly explicitly states the type of bias filter we are having here. There is some ambiguous information about it. So either the filter as per the data sheet should be GPRG or RGGB. Debier filter according to RGGB, the test pattern color comes in the correct order. In the live stream mode, R and B channel will be inverted. So whatever is red will be blue and whatever is blue will be red. And if I look at the IMX219 driver code in the Linux repository, it mentions the Bayer filter to be BGGR. Right now in my FPGA, I am doing the Bayer according to BGGR format, but the problem with BGGR, live image comes perfect, but in the test mode, R and B channel will be inverted. So you will see wherever the R and B channels are involved, the colors will be exchanged. I have no idea why it's like. I will try to look further for the reason. And index number 3 is going to be this text pattern, and on the bottom side you will see there is some grayscale going on. You see the difference on the bottom. Let's move to test pattern number 4. Actually there is no test pattern number 4 from 3. This is how test pattern number 5 looks. Colors are absolutely perfect. If you compare them to the PDF, let's go to next test pattern. Let's go back to the normal image. As I have mentioned earlier, camera sensor does not have any automatic exposure control or any other kind of control for that matter. So you need to control the exposure manually or implement some algorithm to do. Right now there is no algorithm implemented on the FPGA side, but see it for the light. So you can manually set the brightness from here and again, and depending on the scene brightness, let me turn off one more light. It's a little bit lighter now, and you can turn down the brightness. This contrast is currently mapped to the integration time. You can increase or decrease up to a certain limit, but as the integration time directly affects the frame rate, you can only go up to a certain range. As mentioned before, this is the test pattern control. Now let's look at the implementation, how the FPGA modules are implemented. MIPI data comes in from the left side and parallel data outputs on the right side. As an input, MIPI clock and 4 data lanes. What is not shown in this block diagram is I'm sensing one of the clock line in LP mode to be able to detect frames, and one of the data lane is also sensed in the LP mode to detect when the individual lane in the frame starts. This is my rudimentary way to detect when the transmitter is in HS or LP. As all the 4 lanes are more or less in the sync, so I don't need to detect every single lane, so I detect only one of them and let the byte aligner and lane aligner to do their job. First block is the D5 DDR RX block. This is a block I generated from the lattice IP Express, but I did do some modifications on it. The standard IP Express generated DDR block output is a little bit weird and it generates only byte clock. I needed the output clock as well. The byte clock is input clock divided by 4 and output clock is divided by 2. We are having 200 megahertz of clock, which translates to 200 megabyte per second. DDR byte clock will be 50 megahertz and the output clock will be. And second comes these byte aligner, which are applied to every single lane. To answer the question why byte aligners are needed, we need to look at the MIPI timing diagram. This is the timing diagram. Problem is the number of clocks between when the transmitter enters into HS mode and when the first data bit comes. This time is somewhat indefinite, so you can never know what are the byte boundaries. So for each lane to detect when the individual bytes are starting, every single lane has a byte aligner. This byte aligner will output byte aligns data to the lane aligner, and job of the lane aligner to do lane alignment. And what does lane alignment mean in the MIPI is that individual lanes in the MIPI as per the MIPI specification need not to be in the perfect sync, so bytes can arrive with a little bit amount of delay. There is a possibility that we had already received 2 bytes from the first lane and only received 0 byte from second lane. So lane aligner will wait for the sync byte 0xB8 to arrive on each lane. When it starts getting data from all the lanes, only then it will output the 32-bit lane aligned data towards the MIPI CSI packet decoder. MIPI CSI packet decoder looks for the specific packet type, which in our case is a raw 10 packet, hexadecimal code 2B. So it looks for the specific packet code. If you look at it, I have oscilloscope view as well. This is how it looks on the lane 1. This is the oscilloscope view of the lane 1. On channel 1, the clock, channel 2 and 3 are the data lines. This scope capture is after the byte aligner. So this is the packet type we are looking for. Package decoder will look for the 2B package type, and if it has find valid package type, it will output the data towards the raw 10 depacker. Otherwise, it will just ignore that packet altogether. Packet decoder also fetches the packet length from the bus and keep track of how many bytes have come in, maintains the output valid only for the defined number of bytes. Once the next module receives the 32-bit data, it's started to unpack it and wrap them by 4 10-bit pixels, which will translate to 40 bits. Unpacked 40-bit data arrives to the debuyer. Debuyer will put it into RAM and calculate debuyer on it. Output of debuyer is RGB output. It outputs 4 pixels per clock and each color is 10-bit. That 120-bit bus goes to the RGB to YUV converter. RGB to YUV converter takes these 4 pixels and convert them to 64-bit 4-pixel YUV output reformatter. Takes the DDR byte clock on which 64-bit data coming in and takes the output clock from the main DDR RX block, generates the pixel clock and outputs the 32-bit data. F-sync is generated based on the LP signal from the clock. L-sync is generated by the output reformatter. There are definitely some improvements possible at the image quality and at the USB firmware side. I will try to increase the frame rate and the maximum resolution. So if you are interested in this project, you can check back later. Soon I'll be posting more information and there'll be more videos coming. This project is completely open source project. So all the source code for the FPGA, the USB board and the hardware files are available in the GitHub repository. More description about the project you can find on my blog www.circuitvalley.com.